In this video, we're going to look at limits of areas. And in this video, we're just going to be developing the intuitions for how we do this. So here's an infinite summation. It's the sum of reciprocals of squares. It's quite a famous one in maths. And some of you may know that this has a famous limit. And its limit, when summed to infinity, is extraordinarily pi squared over 6. Now, we're not going to prove that result in this video, but what we are going to do is prove that this sequence is convergent, because it's not obvious that it is actually going to converge in the first place. And the technique we're going to use is to compare discrete series like this with continuous integrals. Now, how do we do that? Well, to show that the sequence here converges to something, we're going to show that a sequence of rectangles, the area of a sequence of rectangles, is always smaller than an integral that we can show actually does converge. So here's how we do that. We imagine what these would look like stacked up as rectangles. Well, the rectangle 1, well, we could give it a base of 1 and a height of 1. Now, I know that the scale here is not the same. That's okay. 1 and 1. The next one, 1 over 2 squared. So that is a base of 1 and a height of a quarter. And so on. And then a base of 1/9 and a height, a base of 1 and a height of 1/9, and so on. And what we can do now is we can say, let's compare this to a curve that goes like this, that just skims past each of these points. Now, what is that curve? Well, it's the curve where when x is 1, y is 1 over x squared. And when x is 2, y is 1 over x squared. And when x is 3, y is 1 over x squared. So that is the curve y equals 1 over x squared. Now, I don't want to be evaluating this continuous function all the way down to 0 because it's got that asymptote there. But if I can show that just starting from 1, if I can show that 1 over x squared has a finite area all the way to infinity, well then all of these remaining blocks must have a finite area as well, because they're always sitting under that curve. Similarly, well, not similarly, but then on top of that, all I need to do is say, oh yeah, and there's a +1 at the end, but that's not infinite. So if I can show that 1 over x squared between 1 and infinity is convergent, and I can show that this sequence here is always sitting under it, then we're done. So just to be super clear, what we're going to do here is we're saying that the area that I'm interested in, which is this summation here, is this blue region like this. And the integral I'm going to find is actually everything under the curve, including this blue region as well. So clearly, sorry, that's how ugly this looks. Clearly the red region here is bigger than the blue region. So if the red region is convergent, then the blue region definitely is. So what is the integral of 1 over x squared dx between 1 and infinity? Well, that's pretty easy to do because I can just evaluate -1 over x between 1 and infinity. Subbing in infinity, or rather subbing in a value which tends to infinity, gives me 0. Then minus, so plus 1 over 1 gives me 1. So what I've learnt is the area under the curve 1 over x squared between 1 and infinity is 1. And therefore, I know that this summation must be less than 1 if I start at this point here, which is actually starting here. So here's how I write this out. I can say this sum from 1 to infinity of 1 over r squared minus that first 1 must be less than, strictly less than, the integral which I've just found, which is the integral from 1 to infinity of 1 over x squared dx, which we just found to be 1. So adding 1 to both sides, I've just proved that the sum from 1 to infinity of the reciprocals of the squares must be less than 2. Now, I can do something else clever to find a lower bound as well. I mean, I've shown that it's convergent, and that's important. But if I wanted to actually find some upper and lower bounds on this, I can do that. And I can do it by shifting my rectangles over. Because if instead of slotting that in here, I shift them all over by 1, like this, then you'll see that the rectangles always sit above the area, like the integral area that I found. And what does that prove? Well, it proves that the infinite summation, so the sum from r equals 1 to infinity of 1 over r squared, is actually always bigger than the integral from 1 over x squared from 1 to infinity, and that was 1. So I've shown that it's not only is it less than 2, it's definitely bigger than 1. So I've actually established a lower bound as well. So that's kind of cool. And if you evaluate pi squared over 6, you do indeed find that it is somewhere between 1 and 2. Okay, so that's how we show that a sequence is convergent, by comparing it to an integral that we can evaluate. We can also show that a sequence is divergent by showing that it's always bigger than something that we know actually explodes to infinity. And let's explore this sequence, which famously is divergent. So the sum of the reciprocals, the unsquared reciprocals, is divergent. Now, often this is, we often prove that this is divergent by sort of considering groups of numbers that always add up to more than half, which is a nice proof, but we're going to do this using integration. So we're going to be comparing this sequence to the function 1 over x. And here's how we're going to do it. If you want to show that your sequence is bigger than something, then often we don't start at 0, we start at 1. So it's the difference between this first block here and when we shifted it over by 1. So I'm going to start my first one here. So there's a base of 1 and a height of 1. And I know the scales are not linear, but that's okay. Or they're not the same as each other. So there's 1, there's 2, base of 1, height of 1. So that's got an area of 1. The next one I'd like to have an area of a half. So I have a base of 1 and a height of a half. And the next one, I want to have a base of 1 and a height of a third, and so on. And so this is where my curve slots in, because I just have it coming down here through the left-hand sides. And why does that work? Well, it works because, look, 1 and 1 divided by 1, 2 and 1 divided by 2, 3 and 1 divided by 3, and so on. And what this establishes is that the sequence I'm looking for, so the sum from r equals 1 to infinity of 1 over r, must be greater than the integral from 1 to infinity of 1 over x dx. And it must be bigger than it because every single one of these rectangles is going to poke out here. Now, in this case, that's obvious because this is clearly a decreasing function. In some cases, we actually have to prove that it's a decreasing function first, where that's not obvious. Because if it was not decreasing, this wouldn't be the case. So if it suddenly curved upwards, it might start curving above your rectangles. So what can we do with this? Well, the integral of 1 over x is ln x. And ln x does not, between 1 and infinity is divergent. So we can say that as, what letter have I not used yet? As a tends to infinity, ln a also tends very slowly, but it gets there, to infinity. Therefore, the integral of 1 over x dx from 1 to infinity is divergent. Now, if a sequence is bigger than something which is essentially infinite, then the sequence must be infinite. So we can say that since this here is bigger than that, it means that this sequence is divergent. Now, if we're being really precise, sorry, that is divergent. If we're being really precise, then what I've written doesn't really make sense. So let's write this out a little more formally. We can say, rather than going up to infinity, we can't compare to infinities. What we can say is that for any stopping point n, the sum from r equals 1 to some n of that is always greater than the integral from 1 to n of that. And so what we can really say is that this is divergent as n tends to infinity, and therefore this is divergent as n tends to infinity. So there's no point thinking about upper or lower bounds here. It is divergent. It's bigger than something which is diverging to infinity. So this is the kind of logic we're using in this topic, and we're going to look through a couple of tests we can do and then put it together in some exam problems. So see you in the next video where I'll talk you through some of the tests we can do to test for divergence and convergence.